Hey guys, Dr. A here, and in this video we're going to talk about linear motion and how we describe linear motion in the context of using vector quantities and the interaction between motion and forces using Newtonian mechanics. So we'll do a quick review on the differences between scalars and vectors, and talk about how we use trig to resolve the components of vector quantities. And as I mentioned earlier, looking at the interaction of the system and forces in the context of Newtonian mechanics. So real briefly, if you've taken physics before, or high school level science and math, you'll remember what a scalar quantity is. It's just one that possesses only magnitude. These are things like mass, power, speed, whereas vector quantities actually have both magnitude and a precise direction, such as weight and force. So give you some examples here. This is all the known, I should say all, but some of the scalar quantities that we use in physics as well as biomechanics: distance, speed, acceleration, mass, work, power. In fact, if you look at this first three parameters, the vector equivalents of these scalar quantities would be displacement, velocity, and acceleration. So again, scalar only has magnitude. Vector quantities have both magnitude and direction. Let's just take this dancer for example. She is performing gosh, don't ask me what kind of move. Triple Lutz, that's probably not a move. It's placing a force in this direction here, and this is the point of application. This vector here, this red line, represents the length of it represents the magnitude of the force, and the angle in this case from the horizontal axis gives the direction of that force application. So when we're describing these vectors, remember, as magnitude and direction, we actually have to have a coordinate system. In this case, this is a two-dimensional Cartesian coordinate system to which these vectors can be accurately described. So again, the vector here, length indicates the magnitude. In this case, the angle with respect to the horizontal axis or x-axis represents direction to which that force vector is applied. And because of that, because we know the angle and because we know the magnitude, you can see here we can set it up as a triangle. And because it's set up like a triangle, guess what we can use in order to resolve this vector quantity? That's right, trig. So I think many of you have taken trig before. If not, make sure you review some of the materials that are out there. If you're taking my course for applied biomechanics, I placed a couple videos and some other resources that help you review some of the basic trig. Remember your SOHCAHTOAs. So we'll need this in order to resolve these vector quantities into their respective components. So vector resolution, that is the process in which we resolve these resultant vectors or these vector quantities into their individual components. And for this first set of examples, we're just going to concentrate in the two-dimensional sense, not 3D. Even though in reality we deal with motion in 3 dimensions, we're just going to worry about 2 dimensions, so x and y axis. So a vector can be resolved into those individual horizontal and vertical components, where the horizontal component is parallel to the x-axis and the vertical component is parallel to the y-axis or perpendicular to the x-axis here. So again, I have an example of just say a vector. This could be displacement, velocity, acceleration, and force. And here's a cool thing about vector resolution. It doesn't matter what vector quantity that we're looking at. The only thing that changes is the units and the interpretation of that vector. The way that we resolve the vectors into these individual components is the exact same method. So again, this is a vector. I've got here a coordinate system, a two-dimensional coordinate system, x and y. We can then figure out the horizontal component as well as the vertical component, and making this to a nice right triangle if we knew what the angle was as well as the magnitude of that vector. And just assume, for example, this is a force vector. We can use our SOHCAHTOA. In this case, the adjacent over hypotenuse, so cosine theta is the horizontal component, and sine theta times force is the vertical component. Okay. Real quickly, we want to visualize how this is, and just take your two hands together, point where you want your, force or the velocity or acceleration to point to, and just basically spread out your hands as such so that they are perpendicular to each other, and that would represent the horizontal and vertical components of that specific vectors. So how does this play out in anatomy, in human movement? So we're going to use the elbow joint and the bicep force that it creates about the elbow as an example here. I've got here the elbow joint. Here, let me show, point right here, with the force vector that's created by the biceps muscle. So we all know that the biceps rotates the elbow into flexion, but there's also another component to that. So if we were to establish a local coordinate system, this is a coordinate system attached to the forearm here, we can then decompose that force vector into its rotary component, I showed you here, as well as its horizontal component, which in this example is compressive or stabilizing, and I'll go into specifically how we go about doing that. So if we look at this example, you could see here we draw essentially two parallel lines in order to draw out the rotary component or the vertical component and the horizontal component, or in this case the compressing component, which are the effects of the bicep vector or force vector in this specific example. Okay, so let's take a look. This right here was the position of the elbow that is less than 90 degrees of flexion, and just look at that as probably roughly 45 degrees. I'm just giving you a hypothetical here. So in this position, show here, we know, as I mentioned earlier, we know that the biceps will rotate the elbow into flexion, but it would also, based on its position, compress the joint, because look at the horizontal component and look where it's pointing. It's pointing in the proximal direction with respect to the forearm's coordinate system. So it's pointing towards the elbow joint. So that would tend, the biceps would tend to compress it. What the book likes to call, if you're using the McCluster book, stabilizing. It has a stabilizing effect at this angle. This is at an angle of less than 90 degrees of flexion. Now let's take a look at the other one. This is over 90 degrees. This is probably, I don't know, 120 degrees of elbow flexion. Now we're going to use the same technique, and in fact, in a few minutes here, I'm going to show you exactly how we do that from scratch, step by step. Draw the two parallel lines and figure out what the rotary as well as the horizontal component is at this angle. So you can see here, if we draw this out, you've got the force vector created by the biceps force. It's going to rotate it into elbow flexion. We do know that. But it would also, look at the horizontal component. It is pointing away or distal with respect to the elbow joint. So therefore, it would be distractive in nature or destabilizing. So here, this is below 90 degrees of elbow flexion. That horizontal component is compressive or stabilizing, whereas greater than 90 degrees, it is distractive or destabilizing. And the method that we use, and remember, in all of this example, I didn't go in with any numbers. We didn't use trig just yet. We only use the concept of the right triangle in order to illustrate the direction to which, for example, the horizontal component is pointing. So again, to show you here, this is the biceps force vector. The rotary component was shown right here. That's, you can see that right triangle, and in this position, this angle position, this is just say, I don't know, 45 degrees or 40 degrees of elbow flexion. The horizontal component is pointing towards the elbow. It would tend to compress it. Okay. And see, you can use this. This makes a nice right triangle, and if we knew the angle as well as the resultant force, the magnitude of that, we can then figure out what those horizontal and vertical components are at different positions. So in this next series of video, in the next few minutes, I'll show you exactly how the math in resolving these components can be used to solve for these components. So check this out. Okay, so let's do a little biceps trick. I know, total nerd alert here. So I've got here the four scenarios I just showed you. It's basically defined where the elbow is, right? Elbow flexed at, say, 30 degrees, 60 degrees, at 90, and greater than 90. And before we do any numbers, I just want to show you real quick how that elbow flexion position ultimately affects what the vector of the biceps muscles does in terms of rotating the elbow into flexion, as well as either compressing it or distracting it. So I'm going to use that same scenario, or I'm sorry, parallelogram that I just discussed with you, so that we can find these components before we do any numbers. Okay, so that is as best I can. What I did is I took a ruler and I put this on my iPad and I drew these two parallel lines. The line is essentially parallel to the x-axis of the forearm, or the horizontal axis of the forearm. Remember, coordinate systems can either be global, like the room, or local, like in this case, the forearm. So we're going to use this example so we can figure out which the two components of this biceps muscle, right? That is the vector representing the force created by the biceps muscle, and the length of it is equal to its magnitude. So we're not going to worry about that for now. We just want to show you, I just want to show you how this biceps vector has two components. One component that's perpendicular to that axis, that's the rotary, that rotates the elbow into flexion. That's an easy one. Now the other one, I'm going to use a different color here. The component that's parallel to the horizontal axis goes all the way here, because that's the length of it. And you can see here, this is the triangle. So this, notice the direction of that horizontal component. It's this way. So it's towards the elbow. So as you were to contract that biceps muscle to create elbow flexion at the same time, because at that angle, it would also compress the elbow. It's going towards the elbow itself. Now let's take a look at this example here. Same thing. I'm going to use a different color. Hold on a sec. There we go. I'll draw here, as well as, oops, here. And then I'm going to draw the rotary component of the biceps muscle. And notice how, in this case, the horizontal component is actually pointing away or distal to the elbow. So this would actually create a distracting force, or distractive force. It's pulling on the elbow. In this case, the angle is greater than 90 degrees. Now, what happens if it's a 90 degrees? This is 90 degrees of elbow flexion. Notice here that you really don't have a triangle, because why? This time the vector of the biceps muscle is directly parallel to the vertical axis, or the rotary axis, of the forearm. So there is no distraction or compression force at 90 degrees. There's only rotary, which is the reason why at 90 degrees, you're able to maximize, we call it a lever arm, maximize the torque that's created by your biceps in order to balance, say, a barbell. Now think about it. If you have less than 90 degrees of flexion, as I showed you in this first part, notice how there is a compressive force there, and so you don't, at that angle, you certainly don't get as big of the component on the rotary component of the biceps vector in order to rotate that elbow. So take-home message in this example, or this demonstration, is that the angle of elbow flexion, or the angle of the joint, will ultimately determine the components, because of trig, of the force vector of the muscle in either rotating the elbow or rotating the joint, as well as the compression and distraction load on that joint itself. Okay, so write this down. At less than 90 degrees, we get compression. At 90 degrees, zero distraction or compression. It is all rotary, all rotation, all right? And then at greater than 90 degrees, we get distraction as well. And actually in all of these, obviously, this is all rotary, right? So the rotary component in all four of these examples or of angles, the biceps would obviously flex the elbow, but depending on whether it's greater than, equal, or less than, equal, or greater than 90 degrees will determine whether it's going to be compression or distraction as well. Okay. Okay, so let's now put some numbers here. Let's assume that the force that's created by the biceps has a resultant magnitude of, say, 200 newtons. Okay. As I mentioned in my previous video, or I'm sorry, earlier in this video, the angle in this first scenario of the elbow, let's just say it's 30 degrees. I think that's a pretty safe assumption there. So based on 30 degrees and a magnitude of 200 newtons, we can then calculate both the compressive component as well as the rotary component of this force vector, right? So I'm going to skip the parallelogram and just draw it out myself so we know from earlier that the horizontal component would be compressive in nature, and I'm just going to call that Fx. And the rotary component, which does this, just draw my triangle, we'll call that Fy. Again, this is compression due to the biceps on the elbow, and this is the rotary component of the biceps that would flex the elbow. Okay, so I've got 200 newtons. Now I'm just going to use simple trig in order to calculate. I'll scroll here. You take the resultant force of that vector. And remember SOHCAHTOA, because it's adjacent, you can see right here, that's the adjacent. This is 30 degrees, right? Remember your geometry. So that is cosine 30 degrees. Then you do the math. And what is it for the rotary component? So this again is the compressive component or compression. And this is the rotary component that would flex the elbow when it contracts. Okay. Plugging this number into your calculator, cosine 30 degrees should be 0.866 times that by 200. You get approximately 173 newtons of compression. And for the rotary component, let's say that is sine 30 degrees. I'm just using my calculator on my iPhone. Sine 30 is 0.5. So you should get 100 newtons of rotary. So notice at 30 degrees, the biceps vector or force of the bicep can only create in the rotary direction 100 newtons, and in compression it's 173 newtons. So now think about this position. Do you think it's easier to lift the barbell at 30 degrees or at 90? If you said 90, yeah, it makes sense, right? At 90, you get the full 200 newtons because there's no, at 90 degrees, that vector is directly parallel to the y-axis of the forearm there. So it maximizes that lever arm, maximizes the force that is created by the biceps muscle. Okay, so now let's take a look at another scenario. Let's just say that at this position, the elbow is 45 degrees. And if you're taking my Applied Biomechanics class, you'll see these types of questions on either the assignments or the exams. So I give you these angles. I'll give you the magnitude of the or the resultant vector of the particular muscle. So, and all you got to do is just plug in, use some trig in order to calculate the components. So again, let's just say, for example, this is also 200 newtons, but this time the elbow is flexed at 45 degrees. Actually, oh, this is very important. I should have mentioned this earlier. I'm going to make some room. I apologize for this because I got to make some room. Knowing your applied anatomy, that technically is not 45 degrees of elbow flexion. Remember, if we're looking at our anatomy, this is 0 degrees, right? 0 degrees of elbow flexion, but when someone does this, that's actually 90 plus 45. That's actually 135 degrees of elbow flexion. So if you see that, the 135 degrees of elbow flexion, then you know with respect to the 90, the horizontal, the fixed horizontal, this is 45 degrees. Okay, I'll come back to that in a sec. So let's work this problem out. Now we want to know what the horizontal component, we know that is distraction because it's greater than 90 degrees, 135. And this component here, oops, should draw it here, is the rotary component. And that obviously is going in the vertical direction or the direction perpendicular to the x-axis of the forearm. So if this is 45 degrees, then obviously this is also 45 degrees, right? 45 plus 45, 45 is 90. So easy math. Just work out the problem. If you guys remember this from geometry, trig, Fx is the distraction force or distractive. F times cosine theta, which in this case would be 200 newtons, times cosine 45 degrees. Fy equals sine theta, also 200 newtons, sine 45 degrees. What do you know about trig, about triangles, particularly right triangles when the angle is 45 degrees? Correct, they should be equal. So work out the numbers. What do you guys get? Should be the same for both of them. Okay, so if you work out the math, you'll know that sine 45 degrees is equal to cosine 45 degrees, so you should get the same value for both the distraction force as well as the rotary force at an angle of 135 degrees of elbow flexion. Cool? So more often than not, you have more than one vector, or a system may have more than one vector that's being applied to that system or being pulled in multiple directions. And so we can use vector composition in order to determine the resultant or net vector or net force that's acting on a single vector. And this is sometimes referred to as the resultant vector or the net force if we're using forces as an example for the different types of vectors. So if there's two or more vectors that are acting on a system, then we can sum everything up in order to determine what the net force or the resultant vector is. It's a real simple example. Let's say you got two guys pushing a car. This is the coordinate system here. X is positive, and if we're looking towards the right, and Y is obviously up. So these two guys here, let's just call them Harry and Niall. Harry and Niall is pushing this car here. Harry here is pushing at a force of negative 500 newtons. It's negative because he's pushing in the negative direction. The force is directed negatively, as well as Niall here at 600 newtons. So the net force would be negative 1100 newtons, or 1100 newtons in the negative x direction. Now let's take a look at tug of war. You know what a tug of war is. There you have two teams that are pulling in opposite direction here. Team A, one of the members of that team is pulling at negative 700 newtons, while the other person is pulling at negative 450 newtons. Whereas Team B is pulling at 600 newtons, positive 600 newtons, and positive 650 newtons, respectively, at least according to this coordinate system. So therefore, if you were to sum everything up, you would get a net or resultant force of plus or positive 100 newtons. And so this is 100 newtons pointed in the positive direction, positive x direction, or if you're looking at the screen, towards the right. So how does that work with anatomy? Well, we know that muscle groups all work in synergy. And if we look at a specific muscle group, all of those individual muscle fibers have different pennation angles, they have different lines of action, but when they contract together, they all pull in one direction. A perfect example is the quadriceps. We look at the quadricep, you guys already know the anatomy. You know, you got the rectus femoris, the vasti muscle. They all contract in order to rotate the knee into extension. So I'm going to use a very simple example here, and this is the first math problem that you'll be doing in this lecture. And let's just say that both the rectus femoris and the vasti muscle groups each contract at a force of 15 newtons each. But the difference is the vasti muscle does it at an angle of 20 degrees with respect to the quadriceps line of action. So using trig, we can figure out what the net or resultant quadriceps tendon force by simply adding it all up. So go ahead and figure it out on your own, and we'll come back and check out the answer. Okay, good. So if you use trig, it's pretty simple. The line of action of the rectus femoris is actually parallel, so you don't need to do anything with that. That's 50 newtons. Whereas the vasti muscle, that is the adjacent component of the vasti's resultant force vector there. So that's 20 degrees. That's done at an angle of 20 degrees. So it's 50 times cosine 20 degrees. For each of the vasti muscles, do the math, which this is just simple trig. You should have gotten approximately 144 newtons. So a side note, if you haven't guessed already or you don't know already, a newton is a unit of force, SI units. So we can't really talk about motion or changes in motion without talking about the forces that cause or change this motion of a system. And a system could be the human body itself or a part of the human body. And all of that is governed by Newton's laws of motion, which, as you've taken physics before, or even just a high school level introductory course, you know about, or at least familiar with Newton's laws, 3 laws of motion. So I'm not going to go into detail. In fact, in another video, I talk about Newton's laws of motion in the context of a human movement, say for example the counter movement jump. So the first, second laws, say the law of inertia, law of acceleration, law of action, reaction. So what are the properties of force? By definition, a force is something that a system has or something with the capability or capacity to cause the change a motion of a system. It has direction, it has orientation, it has a point of application, and it has a magnitude. Remember, it's a vector quantity. There is a line of action, which is just simply an imaginary line that extends infinitely along the vector through the tip and tail. So it gives you an idea of the direction to which the force vector is pointing. So if I bring back my dancer here, this dancer is placing a force on the ground right here at a direction that's a certain angle, theta, and the length of that vector here represents the magnitude of the force applied. And then we'll find out later there is according to Newton's third law, there is what's called a ground reaction force that is equal and opposite to that vector that's placed by the ground on the dancer here. So that's the different types of forces out there. An easy one that we all run into every single day because we walk and run and jump is friction. And friction is just the force that exists between two objects that are in contact with each other, and it prevents one system or one object from slipping with respect to the other system. So for example, in walking, What prevents your back foot at toe off from slipping this way is the ground, or a frictional force, that is directed in the opposite direction. That's why you're able to accelerate forward at toe off. And at heel strike, and this is initial contact, this is what initiates the gait cycle here. And what prevents you from slipping forward is also that same horizontal friction force, and allows you to stop your momentum momentarily or slow it down, so that you can move forward into the rest of the gait cycle. So that is friction, and as a function of what's called the coefficient of friction of the surfaces, as well as the force that's perpendicular to that surface. Okay, the other source of force, since we're talking about human movement, is obviously our muscles, right? And if you've taken anatomy and physiology, you know the cross-bridge cycle and what's happening at the sarcomere level between actin and myosin and tropomyosin. This is very fascinating stuff here. So all of that's together creates what's called a contractile force that is a function of the sarcomere cross-bridge here that happens, and all creates that muscular force, and subsequently creates torque about the specific joints about which these muscles span. So I'm not going to go over into details of the muscle mechanics. I have that in a separate lecture, but obviously that is a source of force and torques that cause or change motion. The other one's gravity. We here on Earth are all under the effect of 9.81 meters per second squared, and I should have put negative because that's directed toward the center of the Earth. And so when we're discussing human movement, we cannot ignore the effect of gravity, the acceleration of gravity. So that's an obvious source of force or change in motion. Okay, so the line of gravity for any object will always go through the center of gravity. In fact, this is the person's center of mass. Center of mass is measured in all three directions, or all three planes, and the line of gravity, which is the direction through which the gravitational pull of the Earth will be applied to an object, or to a system in this case, will be directed through that COG. So we call that the center of gravity, and we use the principles of torques and joint moments in order to calculate what that center of gravity location is on the human body. I discussed that in a separate video as well. Now, I talked about Newton's third law. For every action, there is equal and opposite reaction. When you walk, when you run, when you jump, an individual places a force on the Earth, and in reaction, the Earth places a force on you that's equal and opposite to that actual force. So in order for us to accelerate forward, that ground reaction force has to be greater than your weight, or something less than your weight, depending on whether you're decelerating or accelerating, in order to have that change in motion. So when we're discussing all the various types of human movements, we can't ignore the ground reaction force. Now, the ground reaction force, like all other force vectors, are in 3 dimensions. But at least for the initial parts of these lectures, we're going to mainly concentrate on the vertical component of the ground reaction force. Okay, so I have here in this next video an example of how the ground reaction force determines ultimately the acceleration of the body center of gravity during a counter movement jump. So check this out. So I'd like to explain Newton's first, second, and third law in the context of human movement, and what better way to demonstrate that than using what's known as a counter movement jump, as I've shown you here. So this is a biomechanical model of an athlete that came into our biomechanics lab. He got fitted with reflective markers and is jumping on 2 force platforms. These 2 force platforms measure what's known as the ground reaction force, which according to Newton's third law is equal and opposite to the force that an individual makes while he or she is in contact with the ground. So whenever we walk, whenever we run, we jump, whenever we're in contact with the ground, we're placing a force on the Earth. And in reaction to that, the Earth places a force that is directly that is equal and opposite in direction to the force that we place on the ground here. So that is a perfect illustration of Newton's third law. Now, in the first part here, the person is just standing there. And what I show you here on the top right is a graph of the vertical component of the ground reaction force, and here in the bottom right is the vertical component of the acceleration of the person's center of gravity. So I'm going to concentrate here first. The person is just standing there, so his vertical ground reaction force is equal in magnitude to the person's weight, because right now the only force that the person is placing on the earth is his own weight, and we know that the line of gravity, the action of gravity, is towards the center of the earth, which in this case is in a negative z direction, and the ground reaction force is equal and opposite. If you were to add those two up, the net force in this state is equal to 0, which according to Newton's first law, which is the law of inertia, the state of motion will remain in that state, in this case at rest, unless the net force changes, unless the net force is a non-zero, which in this case it isn't. It's equal to 0, so therefore the person's at rest. Newton's first law simply says that a system that is either at rest or moving at a constant velocity will remain so unless acted upon by a net external force that's not equal to 0. So at here, this point, the net force is equal to 0, and then the person moves. Then the person begins to contract his hip extensors, his knee extensors, his plantar flexor. That creates a force on the ground, and in reaction, you can see here that the ground reaction force begins to change. And by Newton's second law, the law of acceleration, which states that the acceleration of his center of gravity is directly proportional to the net force acting on the system, you could see here that it changes. In fact, the first part of the squat here is his center of gravity accelerating towards the ground, or more specifically speeding up towards the ground, and then he slows down as he approaches the end of the squat, and then he accelerates upward so that he takes off and is in the air for a few milliseconds here, and it's governed by 9.81 meters per second squared by gravity, and then he lands. In fact, in a separate video I discuss in detail the significance of the positive and negative acceleration during a counter movement jump. But what I wanted to explain here was Newton's first, second, and third law. I started with Newton's third law first to explain the ground reaction force and how that is a direct reflection of the force that an individual places on the ground. And Newton's first law, when the person is just standing there, for example, so when the net force is equal to 0, we see no acceleration. In fact, the person's at rest. And of course, Newton's second law, which states that the acceleration of the person's center of gravity is directly proportional to the net force imparted on that system, which the only thing changes, because the person doesn't change his weight, is just the ground reaction force.